In this video, I will be discussing about the 2D NMR techniques. So till now, we discuss about 1D NMR, like proton NMR, carbon NMR, those were 1D NMR. So 1D NMR spectroscopy is a simple technique in which we provide 90-degree pulse to sample, which is placed in a uniform magnetic field. As a result, we get a FID signal. To get meaningful data, we apply Fourier transform program on FID to get the desired signal. So data in form of frequency versus intensity is plotted along x-axis and y-axis respectively. So this is FID and this is a frequency domain spectrum. So in 1D we are getting this kind of spectrum. But here graph is actually in 2D because it's between frequency and intensity. But why we call it 1D NMR? So not because of graph, since one of the time domain is changing into frequency dimension. That's why we call it 1D NMR, because here only one time domain converting to frequency domain spectrum. Now what is 2D NMR? So in the 2D NMR, we provide a 90-degree pulse to our sample. Then we wait for 0 microsecond to 5 microsecond depending upon the experiment type. Then we provide again 90-degree pulse, and this time we measure signal as FID. So as a result, we get two FID signals which are plotted with respect to time domain. Then we apply Fourier transform program on FID to get frequency in terms of ppm. But here you can see 2D NMR is a set of nuclear magnetic resonance spectroscopy method which give data plotted in a space defined by two frequency axes rather than one. So here we have frequency on both axes. In 1D spectrum, we have frequency on x-axis and intensity on y-axis, while in 2D, we have frequency spectrum on both the axes. So this is the 2D spectrum. So 2D spectrum are generally divided in two types: homonuclear, where we provide two frequency to same nuclei in sample, like proton-proton correlation spectroscopy or COGI spectroscopy. Heteronuclear, in this we provide two frequency to two different nuclei in this sample, like one is proton, other one is carbon. So we say it heteronuclear correlation spectroscopy or HETCOR. So let's start with the COGI spectroscopy. That's a correlation with the same type of nuclei. So 1H COGI or correlatory spectroscopy is a useful method for determining which signal arises from neighboring proton or which proton are nearby to each other. So that's very important to find that which proton is coupling to which proton. Because if we have very complex molecule which has like so many protons, it's very hard to identify that which proton is coupling to which proton. Because in a small molecule we can simply find it, but in complex molecules it's very difficult. So for complex molecules generally we use 2D techniques. So in this 2D spectrum we have 1H NMR at both axes. Like this also 1H spectrum, this is also 1H spectrum of same molecules. Now how to get the information? So we have to go step by step. First, draw a diagonal line, like a diagonal line from this dot to dot on the left hand side in this way. Now draw a vertical line to know that which dot is belongs to which peaks. Like if we want to get information about this dot and we draw the vertical line like in this way, so this show that this dot belonging to these protons and this dot belonging to a proton. Now we have to draw the horizontal lines from the spot on the diagonal, means from this spot to the off diagonal spot, means for this spots or for this spot. So draw a horizontal line in this way from signal or spots on the diagonal to off diagonal spots. Now spots on horizontal line shows coupling protons corresponding these two spots, means protons corresponding to these spots and protons corresponding to these spots are coupling with each other, means this spots belongs to B proton and this spots belongs to A proton, means A and B are coupling with each other. So in this spots also B is splitting to A proton and A proton is splitting to B proton. In case of C, there is no off diagonal spot, so they are not splitting with the nearby proton with good extent of coupling constant. So this is the structure of the molecule which for which we have this to this spectrum here. So A proton is coupling with B. So this shows that A are nearby to B, and this spot is for aromatic proton. So there is no difference in the coupling constant or difference in the spot. So we are not getting much information about the aromatic protons here. Now come on a second example. That's the isopentyl acetate, which has 6 types of carbons in this molecule, and each carbon is attached either with 1, 2, or 3 protons, except carbon number 6. So let's try to interpret the structure using this 2D spectrum, which has proton NMR at both axes for this molecule. So first we will draw a diagonal from the right hand side to the left hand side. Now start at the upper right hand side of the diagonal line for the protons on carbon 1, means for this spots. This belongs to carbon 1, means this, we are talking about these protons. Now follow the horizontal line to the left of the diagonal peak at A. This tells us that the proton on carbon 1 correlate with the protons on the carbon 2, because this spots A belongs to protons on carbon 2, means for this proton. So means proton on carbon 2 and protons on carbon 1 are coupling with each other. Now look at the diagonal line again. The proton on carbon 3 means these protons, or we are talking about these protons. Following the horizontal line to the left, you will observe 2 off diagonal. If we draw this horizontal line, we will see spot C and spot B on the horizontal line. Means proton 3 are coupling with the proton giving this spot and proton giving spot B. So this spot is coming protons on carbon 2, and this spot is coming due to protons on carbon 4. Means proton on carbon 3 are getting split with the proton on carbon 2 and proton on carbon 4. Now again look closely at the diagonal line at the place labeled 2. Now the line drawn to the right to the off diagonal peak at D and E, D and E. If we draw this horizontal line on the right, we will see 2 spots on this horizontal line, that's a D and E. E belongs to proton on carbon 1, D belongs to proton on carbon 3. Means proton on carbon 2 are getting split with protons on carbon 3 and protons on carbon 1 also. Now inspect the diagonal line at the proton on carbon 6. If we draw horizontal line on the right or left, there is no spot on the horizontal line. So this shows that this signal or this spot belongs to a proton which does not show any splitting with other nearby protons. Means this belonging to this CH3 group, which doesn't show any coupling with the nearby protons. Now for this spots on diagonal, which is 4, which belongs to these protons, if we draw this horizontal line on the right, we will get a signal or spot on this horizontal line, which is we say F. F belongs to proton on carbon 3, means proton on carbon 4 are getting split with proton on carbon 3. So in this way we can correlate between protons on nearby carbons, that how they are splitting with each other. So this information help us to deduce the structure of organic molecules. Now second type of 2D spectroscopy, that's a Hartrott technique, means correlation between 2 different type nuclei. So a 2-dimensional NMR technique which reveals spin-spin coupling between 1H and nuclei other than 1H, such as 13C nuclei. So in this, on one axis, that is y-axis, we have proton NMR, and on the other axis, that is x-axis, we have carbon NMR. So you will have carbon on x-axis and you will have proton on the y-axis for same molecule. Now each spot of intensity on the two-dimensional plot indicate a carbon atom that bears the corresponding proton. So in this carbon spectrum on horizontal line, it's like on X, first if we will see on x-axis, there is a two line, one at this ppm value like around 79 ppm and one peak at 21 ppm. Now in a proton we have two peaks, that's a doublet around 1.56 ppm and this is septet around 4.66 ppm. So means now if we draw a horizontal line from this doublet on the right hand side and now a vertical line from this peak of in carbon NMR towards the spots A, we are seeing that this horizontal and vertical line are matching at this spot A. Means these protons are attached to this carbon. So this showing the correlation between protons giving this doublet and carbon giving this signal at 21 ppm. In same way, if we draw a horizontal line from this septet and a vertical line from this peak in carbon NMR at 79 ppm, we are seeing that these two lines are matching at spot B. This shows that this proton are attached directly to this carbon, which is showing peak at 79 ppm. So in this way, we are able to find the relation between proton and carbon, that which proton is connected to which carbon. So that's also help us to deduce the structure of organic molecules. Again, we will take the example of isopentyl acetate, and here we will see correlation between proton and carbon. In previous slide, we have just seen the correlation between proton and proton. Here we will see correlation between proton and carbon. So on one axis, means on x-axis, we will have carbon NMR for this molecule, and on y-axis, we will have proton NMR for this molecule. Now, if you draw a horizontal line from this peak and a vertical line from the carbon's peaks, like in this way, draw a vertical line from each carbon peak and draw a horizontal line from each peak in proton NMR in this way. Now you see this horizontal line and a vertical lines from this carbon peak are matching at this spot in 2D spectrum. So means this proton are connected to this carbon and this peaks. Now the horizontal line due to this peak in proton NMR matching at this spot 3 with the peak of carbon in this chemical shift value. So this carbon is having this set of protons. So same for this, if we draw this horizontal line and this matching with this vertical line at spot 4, means this proton are connected to this carbon. So in this way we can easily find that which proton or which set of proton is connected to which carbon, and that really help us to find the structure of organic molecule. And thank you very much. Have a very nice day.